let's think about how impressive it is that Newton's laws work at all. So to do that, let's imagine a scenario where we have a really large rock, and we've zoomed into that rock so that we can see all the individual atoms. Now, of course, rocks aren't really made of atoms like this, right? They have trillions and trillions of atoms in them, and those atoms aren't just these little hard, circles as we've drawn them. But it's still a good mental model, right? And that's what this course is all about, is building models. Okay? And so we have this rock, it's a collection of atoms. And let's say it's sitting on the ground, which is also a collection of atoms. And then let's say I'm pushing on the rock. Now, of course, there's one more thing, right? We have air, so we'll have some air particles here. And so this is, kind of more realistic. Again, it's not totally realistic. This is still a model. It's just a much more complicated model than the ones we've looked at so far in class. But what we actually have is all of these little atoms are interacting with each other, right? So we have forces that are coming from the atoms in the black top with the rock, and then again, equal and opposite, we have those coming from the rock back to the black top. We have interactions from the air molecules hitting the rock, and again, from the rock back on the air molecules, we have the force of all the atoms in my hand as I'm pushing the rock pushing back on me, right? And that's not even to talk about all the internal forces, right? All these atoms are pushing and bouncing off against each other, right, all the time. So in a certain sense, it's really remarkable that nature has conspired in such a way where we can take this really, extraordinarily complicated picture, and then we can just draw something as simple as having ground, just drawing a rectangle on top of it, and call that a mass. And then we say that, I can push with my hand. So we have a force from my hand on the rock. We have a force from a drag force on the rock. And we have a force of the ground on the rock. So this complicated picture of trillions and trillions of interactions gets simplified into this one thing, this very simple picture, and then we can draw, again, we'll draw our force diagram here. So we have the force of the ground on the rock. Sometimes we just call this the normal force. We have the force for me pushing the rock. So this is the force of my hand on the rock. And for the most part, we ignore drag in this class, but air, which is basically air resistance. But there would be a very small drag force. There would also be a frictional force pushing against it, which we'll talk about actually in the next unit. And so we have all these forces, but this really complicated picture, right, where we had trillions and trillions of interactions, is just boiled down to this. And in a certain sense, almost every problem we do for the rest of the semester just comes down to this diagram, right? Maybe a picture like this. So as the semester goes on, you're gonna get problems, and in those problems, they're gonna have made this seem a lot more complicated than it really is. Essentially, they all boil down to just having some mass with a bunch of forces acting on it and trying to figure out with all those forces summed together what it's doing. And that's 80 to 90% of the rest of the semester is we're going to take a situation like this. We're going to draw a silly hat on it. We're going to dress it up so it doesn't look like something as simple as this. But in the end, this is what almost every problem we do for the rest of the semester is going to boil down to. And so in a certain sense, it's really remarkable that we can take, an extraordinarily complicated physical system, model it as something so simple, and be able to get results that work. And that's what we'll continue to do for the rest of the semester.